Welcome to everybody. Thank you for joining us tonight. I'm Rafaela Marbuti. I'm a professor in the Physics and Astronomy department here at Northwestern, and tonight I'm extremely excited and honored to introduce our speaker, Andy Connolly. So Andrew is a professor at the University of Washington and director of the Dirac Institute. He's also a close friend of us, a close friend of CIERA. CIERA is a Center for Interdisciplinary Exploration and Research in Astrophysics. And Andy serves as chair of the board of advisors for our program of ideas. So we have a program that is supposed to train the next generation of scientists in data-driven discoveries. And here is where Andrew is actually one of the pioneers of this field. How do we make discoveries out of data that are flowing now at a rate and volume that is completely unprecedented? So with no further ado, Andy Connolly, thank you so much.
Thank you, Rafaela. That's a lovely introduction. It's a great pleasure to be here. I've particularly been enjoying the thunderstorms in Seattle, where I reside. We just get continuous drizzle, and it gets a bit tiresome after a while. So seeing the actual impact of these storms has been a lot of fun, as well as the meeting that I've been attending. So what I thought I'd do tonight is to tell you a little bit about the experiments and missions that are going to change our understanding of the universe and change it in ways that are fundamental, from the discovery of new objects through to understanding the properties of dark energy and dark matter. And what I thought I would do is, if you went out into the night sky, away from the city lights of Chicago, and particularly if you went out on a warm summer's night and looked up at the sky, you might actually see this great band of stars crossing the sky. And interspersed throughout these stars, you see these great lanes of dust. And dust, not like the dust that you find under your sofa in the living room, but dust made up of carbon and silicon, the remnants of generations of the formation of the birth and death of stars. And if you went outside and you allowed your eyes to actually adapt to the darkness, and it takes about an hour to adapt fully to the night sky, then the stars begin to emerge, and you begin to see patterns and structure within these stars, these patterns and structures that we refer to as the constellations. Constellations that have been used by many hundreds of years, if not thousands of years of culture, different cultures actually using them to navigate as people moved across the earth. And before the advent of Netflix and Amazon Prime and Hulu, we actually used to look at these stars, and we used to look at the structure, and we draw pictures on the sky. And the pictures that we drew, they were drawn by Johannes Hevelius back in the 1650s, showed the great bear Ursa Major as it strode across the sky, striding towards the constellation of Lynx on the right-hand side. I think today we lack some of the imagination, and so instead of these great pictures, we have stick figures. But even with the stick figures, you can still see the structure in the constellation. You can still see the great clouds, we would call it back in England, or the Big Dipper, and the two great stars on the right-hand side. Let's see if I can get this. On the right-hand side, as they point up towards Polaris, the pole star. Now, if you took a telescope and you began to look just to the north of the great star here, the great star Dove, if we took a telescope and we zoomed in to just to the north of this star, Dove, that was named by the great Arabic scholars and astronomers, named after the Arabic word for the bear. And if we begin to zoom in, then it's not just stars that we see, it's also galaxies. Galaxies that emerge, such as the Messier object, M82. And M82, also known as the Cigar Galaxy, that has been twisted and warped through its gravitational interactions with the nearby galaxy M81. And this twisting and warping and distorting of the galaxy causes stars to form. And so if we look at M82, we find that there are great plumes of gas and dust being spread out into the universe that have been generated by the stars, 10 times as many stars being formed in M82 as we have in our own galaxy. If you were to zoom into M82, and you did that about 4.5 million years ago, then the time when on the Earth was the time when the ancestors to the humans were beginning to separate from the ancestors to the chimpanzees and move on their individual evolutionary tracks. If you zoomed into M82, these 11.5 million years ago, you might have found a small and nondescript star, a star that had long since burned up its hydrogen and helium, burning up the hydrogen and helium and then slowly collapsing down so that it was only supported by the electrons in that star. This small star, a dwarf star, this small star, a white dwarf, destined really to just fade away, slowly fading from view. But the interesting thing about this small white dwarf is that even though it's small, it's still massive, the size of the Earth, and yet the mass of the Sun. And so the gravitational force on the surface of that star will be 400,000 times that on the Earth. And so this gravitational pull from this star began to draw gas from its companion. This star wasn't on its own, it existed as a binary. And as that gas came through, it slowly spiraled down until it moved or fell onto the surface of the star. And as it spirals down, temperature grows, the pressure grows, the temperature grows, and the particles within that gas begin to move more quickly. And the quicker they move, they begin to collide. And the hotter that it gets, the more that they collide, until eventually they fuse, they have collide with sufficient energy that they can begin to fuse, turning hydrogen into helium, releasing a small amount of energy. Now, normally what happens when you increase the temperature is that gases tend to expand. And this is the normal thing that happens when you have something like a hot air balloon. We increase the temperature of the air in that balloon, the balloon expands, becomes less dense, and rises into the air. In fact, a few years ago, I told my young son that the reason that I was getting larger with time was not that I was getting fatter, it was simply that my body was responding to global warming. And so as the Earth got warmer, then I naturally expanded to account for that. I get the sense that you were as skeptical as he was at the time. But on this small dwarf-like star, because of the gravity, because it's 400,000 times more gravity than you would find on the surface of the Earth, then the gas can't expand. And so this temperature increases. And as the temperature increases, the gas begins to interact, and the more that it interacts, the more that it fuses, and eventually we get this large thermonuclear runaway, where the star actually explodes, generating a supernova. A supernova that was as bright as the rest of the stars in the M82, within about a factor of 10, so 10 times less bright than all of the stars in M82, spewing this vast amount of material out into the surrounding universe. 11.5 million years later, a professor in the University of London, just teaching how we observe stars, working in London with exactly the same sky conditions that we have in Chicago, chasing a hole in the cloud, observed this event. I could observe the supernova and watch the supernova and could see how its shock waves would expand through the galaxy. Studying a supernova 11.5 million light years away. So when we think about astronomy, we often think that astronomy, the universe never changes. that is 13.7 billion years old, and yet nothing changes. We see the constellations are different as a function of the time of the year, but it has been there forever, and it will continue to be there forever. But the reality is that in astronomy, everything is about time. Everything that we see, everything that we interact with is all about time, because we interact with it in the past. So when you watch me give this talk, you see images that arrive 20 billionths to the second after I've finished giving the presentation. The sound comes 1.3 milliseconds later. Everything that we do, everything that we interact with is in the past. We are essentially historians. And in astronomy, we have the same, in astronomy, it's the same way. We can't observe things, we observe things in the past, and because we observe things in the past, we can build models to predict what happens in the future. But everything that we do is observing the past. And the difference in astronomy is that we do this at a large scale. So it takes 1.3 seconds for the light from the moon to reach the Earth. The light from the moon is just reflected sunlight. 8 minutes and 20 seconds for a photon to go from the sun to the Earth. It takes about 1 million seconds for a photon that is created in the center of the sun to slowly work its way out to the surface, and then just 8 minutes and 20 seconds to reach us on the Earth. The sun could have stopped shining 8 minutes ago. We still have 20 seconds to realize that we should have worn another layer of clothes. And the outer solar system, we have spacecraft that produce these incredible images of the planet Pluto, or the dwarf planet Pluto, the New Horizons spacecraft. It took 5 hours, 5.5 hours for the signal to go back from Pluto to the Earth. It takes 25 minutes to send a signal from the Earth to Mars and back. And this is why we can't drive the Mars rovers in real time. The nearest star to us, Alpha Centauri, or Centauri Proxima, 4 light years away. We're beginning to look at significant times back into the past. The nearest galaxy to us, M31, the galaxy Andromeda, 2.6 million years ago. When we look at the light of that galaxy, we're looking back to times that correspond to the age of some of the largest stars in our universe. The nearest galaxies that you see, and this is a set of galaxies that have been observed in a small survey, 460 million light years in the past. The most distant galaxy that we've observed today, the light from that galaxy takes 12.8 billion years to reach us. So when we look at the galaxy, we're looking at the universe in its infancy. In fact, if you went out to the night and away from the bright lights of Chicago, and you lay on your back and you looked towards the Orion Nebula, you could sit there without blinking for 5 nights, just looking up at the sky. A photon from that distant galaxy, 12.8 billion years ago, will enter your eye. You won't detect it, but we've been continuously bathed in starlight from the distant universe. So today, with the experiments that we have, with the telescopes and the satellites and the missions, we can look back at the universe as it looked 300,000 years after the Big Bang. And if we look at this universe, at a time when the universe had cooled so the protons and the electrons were cool enough that finally they could combine, turning the universe into a transparent universe that we could finally see. And if you look at this picture, the contrast in this picture is set up so it's 1 part, you can see fluctuations of 1 part in 100,000. And that means that the change in the density of material from one side of the universe to the other is equivalent to going to Soldier Field, filling it with 100,000 people, and reaching in and taking one person out and putting them back in. That's how smooth the distribution of matter is. Now, because we can make these measurements, because we can measure the properties of stars and galaxies from the present day all the way back to 300,000 years after the Big Bang. We can build our models that not just explain what we see, but could potentially predict the future. So now if we run the universe forward, then the gas under gravity begins to collapse. And as it collapses, the temperature increases. And as the temperature increases, the particles begin to move faster. And the faster they move, the faster they collide. And eventually they reach a point where the collision is sufficient to start fusion, the generation of the first set of stars. But gravity doesn't just occur on scales of a star. It occurs on scales of galaxies and clusters of galaxies and superclusters of galaxies, and this cosmic web of structure that extends hundreds of millions of light years across. The formation of the structure that you see only takes about 1 billion years to go from that smooth distribution of 1 part in 100,000 to the filaments and the galaxies that you'd see today. Gas flows down these filaments, colliding and merging, building up the galaxies like the Milky Way. And as we see this, and we take these observations, and we look at the sky, and we build the models, one of the questions we have to address is, why should we care? The larger structures that form, how quickly they form, whether structure forms from the smallest objects that build up into larger objects, or whether it starts with large objects that break up into the smaller galaxies that we see. The answers to how this structure forms is driven by dark energy and dark matter, and the gas in the galaxies. And not just the amount of dark energy and dark matter, but what that dark energy and dark matter might be. On the largest scales that we have this cosmic battle between gravity trying to cause things to collapse down and dark energy driving things apart. And so if we can measure the structure in our universe, then we can treat our universe as a laboratory. A laboratory that works at scales that we will never reach on the Earth, even with the largest particle accelerators that we have in Switzerland at CIERA. And if we can think about how this structure forms, we can begin to answer the questions about what is dark energy? Will the universe expand forever? Was Einstein right? Do we know everything about gravity, or do we have to change our understanding? Are there particles, new fundamental particles that we are still to discover? Are we just one universe or just one of many? And the way that we answer these questions is using the same physical observations that you make every day on Earth. So when you see a car driving off and its headlights dimming, or you go to the tide pools and you see the shimmering of light in those tide pools, these are the observations that we make in astronomy, but just at a much larger scale. Stars are born and die, like the supernova in M82. Stars that explode, this type 1a supernova, we found through observations that they all appear to have the same brightness. And so now, if they have the same intrinsic brightness, we can look at how they dim with distance to give us a measure of distance to distant galaxies. And this is the measurement that was done by 2 groups of astronomers in the early 2000s, using just a handful of supernovae, showing that those supernovae were slightly too dim, and so slightly too far away, requiring a universe that wasn't just expanding, but whose expansion was accelerating. Just 40-odd supernovae that uncovered a component in our universe that we now call dark energy, a component in our universe that makes up 73% of the energy budget of our universe, from 40-odd supernovae. To give you an understanding of what an impact this has and has had on our theories of the universe, well, as physicists, we always like to work with the back of the envelope. So if we were to calculate, using the back of the envelope, how much dark energy would I expect to find in the universe, then the calculation that I get is wrong, is too large, by a factor of 10 to the 120. Now that isn't 120, that's 1 with 120 zeros. And I think you would agree that that's so bad it's not even wrong. If we were to take all of our latest theories on the early universe and cosmology, and were to recalculate how much dark energy we expect to see, our best guess predicts a value that's too large by about 10 to the 60. It's still wrong. So a friend of mine once asked me, how can you be so excited about working on something when you're so completely wrong? And I said, what's interesting to me is the discoveries that we make over the next 10 years may result in theories of the universe that are hard to understand, that challenge our understanding. But eventually, as we get insight into how the physics of our universe works, we may come up with theories that explain gravity and quantum mechanics and electromagnetism and the nuclear forces, and bring them together into some simple and beautiful theory that allows us to explain the evolution of our universe. And this is what we want to do. So the question is, how do we get there? How do we move to a point where we haven't just discovered dark energy, but we begin to understand what that dark energy might be? Well, we know when we look at the structure in our universe, that how large a structure is, or how quickly it collapses, is determined by the amount of dark energy and dark matter, and the properties of those dark energy, or that dark energy and dark matter. So if we want to look and to understand what dark energy might be, there are only 3 things that we have to do. We have to be able to measure the mass of the universe. We have to be able to do this for galaxies that are 6 billion light years away. And we have to do this just by looking at it. Now that seems pretty straightforward. So how actually might I make that measurement? Well, it turns out with the distant supernovae, we said as we looked at the brightness of a car light as it dimmed as it moved into the distance, was the same way that we measured the dimming of supernovae as they appeared in more distant galaxies. Well, we can measure the structure and the mass of our universe using the effects that we see when we go to the swimming pool or the tide pools. If you look at the bottom of the swimming pool, you see all of this flickering light. We call these flickering lights the caustics. The water bends the light, it refracts the light. The very different waves and heights of the water means that the light gets refracted or bent in different ways. So by bending the light, we can bring it into concentrations. And we can begin to see these concentrations or bright lights or caustics on the bottom of the swimming pool. The water acts like a lens. The lens concentrates the light. And the height of the water determines how much concentration we see. If we look at the bottom of the pool, or the tiles on the bottom of the swimming pool, we see that they undulate and change. The shape of the swimming pool is also being lensed or bent. The light from the bottom of the swimming pool is being bent by the height of the waves on the top of the pool. No waves, no shimmering effect. If we could measure the distortion of these tiles on the bottom of the pool, we might be able to measure the height of the water or the height of the waves in the swimming pool. So there are 2 problems with this when we want to apply it to astronomy. We know that light gets bent by mass. It's one of the fundamental principles that came out of general relativity. We know that mass will distort the images of galaxies in the background. But if you go out into the night sky, and you'll have to take this on faith because I am an astronomer and I have been an astronomer for at least 30 years. If you go out into the night sky, or go out into the night and look at the sky, even if you're a long way away from the lights of Chicago, even if you allow your eyes to adapt for an hour, the sky does not look like the tiles on the bottom of the swimming pool. The second problem is that even if we had this beautiful grid of stars and galaxies, then the mass that we get from integrating up all of the mass from here out to billions of light years away, all of this beautiful structure, even if that existed, it would distort this image by this amount. So the mass of the universe is sufficient to distort the average galaxy in our universe by about 1%. So a tiny distortion to the shape. So in order for us to be able to measure and map out the mass of our universe, what we need to happen is to look at densities of galaxies that are billions or billions of galaxies. And for each galaxy that we see, it gets distorted slightly by the mass. And if we can average over thousands of galaxies, we can begin to map out all of the distortions due to the mass that we see underneath. And this means that if we are to understand dark energy, if we are to map the mass within our own universe, if we are to see how mass changes through gravity and dark energy as a function of time, we need to be able to observe billions of galaxies. At least 4 billion galaxies is the goal that we want to be able to measure over the next 10 years. And so how can we do this? Well, the only way that we can actually measure these galaxies is if we were to take a massive survey of the night sky. And so we build a telescope, such as the Large Synoptic Survey Telescope, or the LSST. This telescope will map out our universe in unprecedented scale and in unprecedented detail over the next 10 years. This shows you an image of the LSST that was taken about a month ago. You can see it emerging from the mountains in northern Chile, just south of the Atacama Desert. The picture up here is a picture of the solar eclipse that was slowly setting over the site in Chile, a few weeks ago. And so we built this telescope, the LSST, to map out the distribution of stars and galaxies within our Milky Way in the universe. And to do this, we need 3 components. We need a telescope, we need a mirror, and we need a camera. And the telescope of this project is shown here. This project has taken about 15 years from design to completion of construction. It will take another 10 years from that to undertake the survey. And the total cost of this project will be about $1 billion. So what I'd like to do is to spend a little bit of time to show you how we go from an idea to an instrument capable of detecting billions of stars and galaxies on the night sky. So the telescope, the first idea for this telescope started back in 1998 with a simple design, well, maybe less simple than that. The simple design on the back of an envelope showing a telescope that can image 3 degrees on the sky at a single sitting. The telescope was then refined and improved over time, changing the number of mirrors that we need, changing the design of these mirrors so that we could see as large an area on the sky as we can, building a telescope that's squat and compact so that it could move quickly and move from one part of the sky to the next, building a telescope that could be constructed. And this project was a combination of public and private finances. So the initial funding for this telescope was provided by funding from Charles Simonyi and Bill Gates, the Microsoft billionaires. And so they were the ones who provided the funding to be able to design this telescope, to show that it could actually do the science that we wanted. And then in 2014, when the National Science Foundation and the Department of Energy selected this project, the construction began. And today, this construction of the mirror, of the structure that will support the mirror and the camera, was completed in Spain a few weeks ago. And this great structure that you see, built by hundreds of people, has been disassembled and placed onto a ship and is now sailing across the Atlantic, aiming for northern Chile through the Panama Canal, where it will be reconstructed within that structure that I showed you a minute ago. At the bottom of the telescope is a mirror. The mirror is 8.4 meters across, 28 feet. This isn't large compared to the biggest telescopes we're building, telescopes that are 30 meters across, where the dome for that telescope would be the size of a basketball stadium. This is a telescope that's relatively small, and yet is still 30 tons of glass to make up the optical components for this telescope. And so here you see, back in 2008, loading up the mold for this telescope before the glass was heated up to 2,700 degrees Fahrenheit. And then the glass began to melt. And this whole structure was rotated to keep the shape of this mirror. And then it was cooled, and it's cooled slowly so that we don't get any stresses in the mirror. And then we get what we call a mirror blank coming out. And for 7 years, it was ground and polished under the football stadium at the University of Arizona. 7 years while the University of Arizona continued to lose. That isn't true, by the way. It was about 50-50. 7 years to produce a piece of glass capable of imaging 3 degrees on the side in a single image. And then placed in a crate, shipped down to Chile, put on a truck, driven through a tunnel that has about a foot on either side of the mirror, driven up to the mountain where it sits, waiting to be connected with the telescope support structure. The third component to this telescope is the camera, the largest digital camera ever constructed. 3.2 billion pixels. The same technology you find in the cameras, in a digital camera that you can buy in a high street store. The same size or technology or type of technology that you can find in the sensors that you get in your cell phone. But a camera that's about 5.5 feet across. A camera where a single image would require 1,500 high-definition TV screens just to watch that one image. A camera that gives you the real scale of this camera. This is the lens at the front of the camera, about 5 feet across, one of the largest pieces of glass that is being built as a lens ever constructed. And at the back of the camera, these 3.2 billion pixels are made up of 189 CCDs. CCDs are the same as as I said, the same as you get in your cell phone. CCDs that are black because they absorb most of the light. And if you place this camera and the telescope and the mirror together, then we will get a survey that will start in about 2 years' time. Will start its commissioning phase, the first light from this telescope. And this telescope will image 3 degrees on the sky, about 7 times the width of the full moon, and take an image, and then move, and take an image, and take an image. So every 3 nights, the sky will image the skies above Chile. Each image containing 20 million galaxies. Each image containing thousands of variable stars, and asteroids and comets. Each image slowly mapping its way across the sky. So every point of the sky over a period of 10 years gets observed about 1,000 times. This shows you a picture of the night sky that you'll get from the LSST after 10 years. To put it in context, this is the moon at scale. The width of a single image from the LSST will extend across this screen. If you were to compare it to the Hubble Space Telescope, 3,000 Hubble Space Telescope images are required to map out one image from the LSST. The numbers are extraordinary. Every image will detect about 10,000 variable or moving or transient or new sources on the sky. 10 million variable, moving, transient sources detected each night. Over 10 years, 37 billion stars and galaxies. Each galaxy and star observed 1,000 times. 7 trillion measurements of stars and galaxies in the night sky. And the most remarkable thing about this is that the data become public. They're available to scientists, they're available to researchers, they're available to students, whether high school students or undergraduates or graduate students. All of these data become public to the US community and become public almost instantly. And so the interesting part that we face now, as we try to understand how we make sense of our universe, how we understand the nature of dark matter and dark energy, how we understand why stars are born and die, is that it's not just about the data. We know that the LSST will generate billions of observations of stars and galaxies, generating hundreds of petabytes of images. But if you compare that with today's technology companies, with Google or Twitter or Amazon or Microsoft, every day, every minute of the day, users watch 4 million or 4.5 million videos. Every day, people on Earth, every minute of the day, undertake 4.5 million Google searches. On Instagram, 1.7 million likes. There's a huge amount of data and a huge amount of interaction with this data. And so the scale of the astronomical data set, even though we're creating the equivalent of mapping the human genome, but now mapping the universe, is tiny relative to the scale of data that's been served by technology companies today. But what makes this interesting and what makes this different is that when we want to search through the data, we have to be right. And if we're not right, we have to know how wrong we are. Because if you are searching through vast amounts of data, looking for the 20 or 40 supernova that may change our understanding of dark energy, and what you come across is not supernova, then we're not making use of the data. If you're searching for cats licking lollipops and you come across 1 billion stars and galaxies, that is also not successful. So the challenge that we face today is how do we make sense of the data? How do we make sense of the billions of observations of stars and galaxies? Now, if you look at the data in astronomy today, then we find that the amount of data that we're collecting doubles every year. But the interesting thing is the amount of computational power that we have access to doubles every 18 months through what we call Moore's law. Whether Moore's law is the number of cores in a computer or the number of machines that we can afford to buy, or the number of transistors as it was originally specified. But the fact that these track each other means that we can continue to collect the amount of data that we need. And we can process it and store it and make available. The fact that they're not quite the same, we make up for by running our processing on thousands of machines. The LSST, by the end of its operations, will be running on about 100,000 processors just to keep up with the data. What's challenging for us is while the volume of data doubles every year, and while our computational power doubles every 18 months, our human cognitive capacity, our ability to make sense of the data, does not double every year. In In fact, if you watch social media, you'd wonder whether it goes up or down. And so the challenge that we face today is not the one of collecting data or processing data. It's the one of the human mind thinking of the questions that we can ask, thinking of the ways that we interact with data, thinking about how do we make sense of the information that's contained in these hundreds of petabytes of information, of data. It is more than just computers. It is our ideas and how we apply these ideas to the data sets of the next decade. And if we can do this, if we can make sense of our universe, if we can make sense of the data, if we can make discoveries just from a few tens of supernovae, or discoveries from billions of stars and billions of galaxies, then maybe we can begin to unravel the formation and the evolution of our universe from the present day out to 300,000 years after the Big Bang. Searching through our universe through the 13.7 billion years, uncovering the physics that explains how it formed, and how galaxies formed, and how the solar system formed. And that will be an incredible legacy from a survey that's going to map the stars. Thank you.
Thank you, Andy. So we have a little bit of time for questions, if the audience have some. Yeah, we do many. We have many. So let's start from here.
Yeah, it's the data as it accumulates or as it builds. Will you be able to see through? Will you be able to see the graphics of the birth of these patterns, possibly, or?
So the really interesting thing about astronomy is that when we think about time, what happens is the further we look back, the further we're looking back in time. So while we don't see the an object, a galaxy or a star many times, what we do see are different populations of stars and galaxies as a function of time. And so we can map out what the structure in our universe looked like today. And then if we look back, say, 1 billion years in time, we can map out what the structure looked like 1 billion years ago. And then we can map it out 10 billion years ago. And so what we can end up doing is to say, what are the largest structures in the universe at 1 billion years ago? What are the largest structures at 10 billion years ago? How many galaxies are there 10 billion years ago compared to today? How many clusters of galaxies? And it's this statistical measurements of the properties of our universe and how they change is what we will map to our theories. And that's how we begin to unravel the formation processes of the universe.
Interesting. Is there a supercomputer that's affiliated with the telescope itself, or does that data go to some of these other big machines?
So the data are taken in northern Chile. They're shipped down to processing or a base facility, and then the data get moved through to Brazil, and then up through to Miami, and then from Miami the data gets shifted over to Illinois, to the National Supercomputing Center, NCSA, at the University of Illinois, and that's where we process the data. And the data that we take, we have to be able to process within 60 seconds of an observation being completed in order to find anything that's changed or moved on the sky. And so it takes about 2 seconds to move all of that data from Chile all the way up to Illinois, where the supercomputer center with the tens and eventually hundreds of thousands of processors will actually analyze the data in real time.
So you simulated all this before it was built, right? To make sure that all this stuff flows, or is it just...
No, we're just hoping that it works. No, we've run a lot of tests, and then continuously through the development and construction, you're continuously modeling what the telescope should look like, how the images that you see get modified by the atmosphere, how you can process those images, how you can measure the shapes of galaxies, and whether those shapes are measured accurately enough to measure dark energy. And this is continuously refining the processing, the algorithms, the engineering to move the data around. And yet it's still terrifying that it's only 2 years away.
I have a two-part question. My first question, in the very last graphic that you showed, it only talked about dark matter at the most recent point. Is the current theory that dark matter, dark energy, did not exist before that, or?
That's a really great question. I think one of the biggest open questions we have about, for example, dark energy is the energy density of the universe constant or not? Because the basic idea when the astronomers back in 2000 actually discovered dark energy, the idea was that there was this constant energy density that continued to drive the expansion of the universe. Right, so as normally what happens is, as you say, if I took a ball and I threw it up into the sky, up into the air, it would slow because it does work against gravity. But with this constant energy density, it's continuously driving the universe apart. So the real question that we want to answer, one of the first questions we want to answer is it constant or not? If it's constant, we already have theories that can't explain it to a factor of 10 to the 60. If it's not constant and it evolves with time, it opens up whole new ideas associated with physics. It could mean that we don't understand gravity. It could mean that gravity works differently on very large scales. And so it really could transform our understanding of the universe. And then on dark matter, so on dark matter, we believe that the dark matter in the universe has been present throughout the universe, throughout the majority of the age of the universe. We think that one of the really interesting ways of actually measuring the properties of dark matter is to essentially weigh our own galaxy. Because if we can weigh our own galaxy, we can measure how much mass is within the galaxy. We can see how many stars there are, and we can compare the amount of mass in dark matter to the amount of light that we can actually see. And also how our galaxy formed, and how quickly it formed, and how it merged with other galaxies may actually tell us something about the properties of dark matter, whether it is some sort of interactive or non-interactive particle.
My second question, which is, so I'm not a physicist, but I'm really fascinated by modified Newtonian mechanics as a way to explain what we've seen on dark energy. Could that also explain what you're talking about, or?
I think the ideas behind modified gravity, I mean, there are two different variants of modified gravity. The ones that people particularly work on small scales, maybe explains the dark matter within our own universe, within our own galaxy. And then there are modifications to gravity on very large scales. I think the modifications to gravity on very large scales are very open. I mean, the ideas behind them, the amount of data that we need to really test them, are questions that we will address over the next 10 years or so. I think the question about modified gravity explaining dark matter within our own galaxy itself, I think at the moment it is challenging to make that model work. For example, there are observations of clusters of galaxies that merge and pass through one another, and these seem to be consistent with dark matter and moving with the actual stars, and not consistent with having some change to gravity on the scales of our own galaxy.
Thank you.
Yes, let's take that question.
Thank you for the presentation. Thank you for the presentation. You began by mentioning like how long it takes for a photon to reach the sun, and like how many years away like it takes for like these galaxies are based on how long it takes like for light to reach us. And then you went on to the swimming pool and how light can bend about hours. So I mean, how do we know exactly how many years these are away? Haven't they been bent by the lights. And my other question is, what is your opinion on these arguments that claim that dark matter doesn't exist?
So the amount of bending of light that we see in, if we're looking at lensed galaxies, is a really interesting question. We can model the amount that we think the light gets bent, and it's a small amount. I've said that the distortion due to a galaxy just from the structure within our universe is about 1%. And so that changes the travel time for the light to scales that we've measured up to, say, about a year or a couple of years. So when you're thinking about that a few years compared to the 5 billion years to the distance of the galaxy, it's a very small effect. And that's why it's so hard to actually measure these small effects. In terms of dark matter, I think most of the observations that we have today demonstrate that dark matter or something exists that operates light matter that we can't see. I mean, when we call it dark matter, light dark energy, it's just a name that's trying to explain an observation that we're seeing. But I think the evidence for dark matter in terms of how rapidly our own galaxy rotates, or in terms of how rapidly structure forms in the universe, is very convincing. What isn't clear at the moment is what that dark matter might be. And there are experiments at the bottoms of mines to try and actually detect the recoil from a dark matter particle actually hitting an object. And these are incredibly interesting experiments. And we're beginning, I remember the experiment started when a friend of mine was working on these experiments when I was a graduate student about a long time ago. And over the 25 to 30 years, the original experiment that he was building was 1,000,000 times less sensitive than was needed to detect the current models of dark matter, to actually be detecting a particle. So he was working on an experiment that would never work, that he knew would never work, and would take another 10 or 20 years to get to a point where you could have even the hope of detecting dark matter. But I think what's being shown from experiments like LIGO, where they had the same sort of experiment where they were making measurements and developing technology that they knew would never detect gravitational waves, and by progressively improving the sensitivity of these experiments over 10s and 20 years of investment and continuous investment into something that is so important that we understand, so critical to our understanding of the universe, that it's worth these progressive investments and improvements over time, that now we're at the point where the sensitivity of these experiments should be able to detect many of the candidates that we have for dark matter within the next 10 years or so. And so a 20-year investment to get to the threshold of being trying to detect dark matter, it may turn out that 10 years from now we detect nothing. But that's all equally exciting. It means it changes our models for physics. But at the moment, I think there's strong evidence for dark matter. We just are excited to find out what that dark matter might be.
So time for a couple of more questions. We'll take one there.
The instrument that you showed us that you're installing in Chile, are you suggesting that that instrument may be able to go back far enough in time to see something about the beginning of the Big Bang, the first 300,000 years? And if so, what part of the spectrum would you expect to see that in? Or do we need something like BICEP, the thing that... Okay.
Right, so this telescope is an optical telescope, so it observes invisible wavelengths. So from the ultraviolet, so the ultraviolet cutoff is determined by the transmissivity of the atmosphere. And then the infrared cutoff, which is about 1 micron, is determined by the fact that the devices that we detect photons with are made of silicon, and silicon goes transparent at about 1 micron, so the photons just pass straight through the detectors, you can't detect them. So we are within the visible light. So we will only measure objects back to, depending on the most distant galaxies that we see, back to 12, maybe 13 billion years back in time. So it won't get back to the point of the time when we make measurements from the cosmic microwave background, which are using radio telescopes, as you mentioned, with experiments like BICEP. But what you can do is, if you make measurements about the evolution of structure in the universe over 13 billion years, you can infer what the properties of the universe was all the way back to possibly even to inflationary times. And so that is one of the things that is important about these sorts of experiments. I can measure properties today about our Milky Way, and it can tell you about the last 10 or 12 billion years of the evolution of that Milky Way. Because we know stars can last for billions of years, and we know about how long the star formation phase might exist. So while we won't actually measure, we'll only measure to about 12 or 13 billion years back in time, we can use that to constrain many of the models for cosmology.
So you think that radio will be where the first 300,000 years will show up?
Yes, so radio is great for measuring from about 300,000 years forward when the universe is transparent, and that goes also through to the first generation of stars, a few million, 100 million years after the Big Bang. And so radio observations are really unique in probing that era. But I think the important aspect is the combination of all of these different sorts of measurements that allows you essentially to lay out the whole timeline and then extend that timeline back to potentially even 10 to the minus 34 of a second after the Big Bang. And so it's putting all of this together, and what makes it so interesting is you have to put together a theory that works across these 13.7 billion years of time in order to, and it has to explain all of it. And if it can explain all of that time baseline, often you can extrapolate it back to the earliest time.
Okay, time for one last question over there. Just like to go to them.
Yeah, you alluded to the dark matter density distribution in the colliding of two galaxies. Is the distribution of the density of dark energy understood, implied, or?
That is a really fascinating question, because at the moment we think that the evidence is that dark energy is uniformly distributed across the universe. We have experiments even with the LSST to probe in great detail on a handful of different positions on the sky. And if you can probe in great detail on a handful of positions, in more detail than the whole of the sky on average, you might be able to see whether dark energy is different from one direction to another. And if that is true, that would mean that dark energy may be clusters on the sky. And that would be a remarkable discovery that wouldn't fit with any of our current physical theories. So because we know so little about it, that is why we have to measure it and because it's so hard to measure, that's why we have to measure it so precisely across the whole of the sky. I mean, most of the theories would say it shouldn't vary, and one of the kind of the principles behind cosmology is that wherever you look on the sky, as long as you're looking at a large enough volume, then the physics should be the same. But we don't know, is the answer. And it's a great experiment. And you should do it with the data.
All right, I'm afraid we have to cut the question time. I would like to thank you again and to thank you so much for this tour in the universe. And I'd like to take this opportunity to say my thank you to the CIERA staff that enabled this event. Big thank you to our students that have been running the mics and all the participants of the conference that joined us tonight. And thank you all for being so enthusiastic about our research. Thank you.